So my name is Roger Oakey, W0TLM. I'm actually a relatively new member to DSES. I think I joined in 2002, and kind of immediately was drawn to the group. I'll make that kind of clear here in a moment. By the way, if you're on Zoom, I'd suggest you turn off your, well, please turn off your audio, but I'd also suggest you turn off your video. That makes things a little bit, refreshes happen a little bit faster for the slides. I don't have any audio in this slide deck, but it certainly helps with audio and video if people have their video off. So I'm here to talk about, very long title, as you mentioned, Deep Space Exploration Society's collaboration with NASA for one-way Doppler measurements tracking. And just a little bit about me, which I'll skip over really quick because a lot of people already know me. I'll just kind of point out this one thing at the bottom is that I consider myself a maker, and DSES has a lot of interesting things going on and building going on. And that's where I got really kind of drawn to it. Is I love building things, making things, inventing things, and they have a lot of need for that down there. So I've kind of gotten involved in DSES for that reason. Actually, more so than amateur radio. So I kind of enjoy working down there. So I should be looking at my my notes here before I go on. So Hans asked me to present the results of our collaboration with NASA with measuring the Doppler shift of Orion's, the Orion capsule's broadcasts. So if I meet what Hans asked for, it's actually a fairly short presentation in that our end product was a date, time, and a frequency for the carrier from the Orion capsule. And that's it. Any questions? So, actually, our collaboration with NASA was quite a journey and an adventure for everyone down there. So, I will revisit those results again, but let me tell you what it took for us to get there. So we'll start over again. So again, we have the collaboration with NASA. This is our 60-foot dish. And up to now, this dish has only been used for what we call deep space receiving, for hydrogen lines, pulsars. We've been doing a lot of radio astronomy, as well as the amateur radio side of things grabs it to do a lot of moon bounce competitions. So that's pretty much our two primary goals, or our two primary uses for the dish. Both of those things are celestial objects. Either we're looking at objects that are within our galaxy or the moon. So suddenly we had to track an artificial object, something that was launched from Earth, which was a completely different use of our antenna than before. So again, what NASA was looking for was for private industry to gather Doppler shift information. Now, if we look at this is kind of an artist's view of the Artemis the Artemis mission, and Artemis was launched, and it did after about a half an orbit, they boosted into a highly elliptical orbit. And it did a number of experiments, and then it came back down, and then they did the translunar injection burn, which sent it off to the moon. And what they wanted to do is they wanted private industry to be able to get this Doppler information. So if you think about it, if you've got 3 points on Earth, and you know when Orion is transmitting something, the Doppler shift plus the time delay for those transmissions, you can actually triangulate where in space Orion is, as well as its velocity vector. So if something were to happen to NASA's Deep Space Network or perhaps they just find out it's cheaper to hire private industry to do some of their work. They would be able to track the capsule or track a capsule in the future. So this is kind of an experiment for NASA. So this is where it started. NASA put out what's called a request for information, or an RFI. Some of you may be familiar with I can get the pointer off here, with RFPs, requests for proposals. The difference between an RFI and an RFP, as far as I can tell, is you don't get paid for an RFI. So this was a totally volunteer effort on our part. And so this came out in August, was the RFI. And by the time October came around, Rick Hambley, raise your hand, Rick, had written the RFI and sent it off to NASA. NASA took their sweet time getting back to us. It was like mid-January or so before we heard back from NASA, like 2 weeks before the first window for launch. This was kind of an ongoing thing with NASA. My theory is that NASA has dealt with like big contractors, the same big contractors, for so long. There's a lot of understood information between the two of them that they weren't really good at communicating some stuff with us small folks. But so this response was in fact accepted by NASA. And if anyone's really interested, you can go to the DSES site, and under projects and under Artemis 2, there's the response to the RFI. There's just a lot of information about our Artemis effort on the website. Again, thanks to Rick, who has been very good at putting up a lot of information that we're doing. So, as I mentioned, the best I can figure out is that NASA's looking for perhaps private industry to take over, or for some kind of backup for their deep space, what they call their deep space network of telescopes. But the question is when you have 230-foot dishes out there in your deep space network, why would you ever really need a backup? You've got 3 sites and all that. So, but what's kind of interesting is that the RFI, NASA's RFI, went out in August. We replied in October, and as if to reinforce the point, NASA had a problem. They destroyed that 230-foot dish that I showed you. What happened is they over-rotated the azimuth. They broke water lines. They broke power lines. They broke their coaxes and all that were going up to the dish itself. So that was kind of interesting for that to happen right in the middle of this. And if anyone, I actually found this, since I deal with a radio telescope, I kind of dug into this report, and it was a very interesting report. You can find it very easily by Googling Deep Space Network antenna accident, and it will come right up. You can see that middle picture down there shows cables wrapped around the hub, and you may not be able to see, people at home probably see, but you may not be able to see here, but there's a doorway with water pouring through it. So their fire suppression system that was up in the in the telescope, basically the pipes were broken. But
Roger, was that Goldstone?
Goldstone, yep.
That thing was built when I was in high school, for crying out loud.
I'm going to address that in just a moment. So there is a final report there. It has lots of detail. You can bring it up and you can read it, or not. There's actually very little of it is redacted. There's a lot of really good information here, and so it's a good report. I'm going to do a little aside here for the too long didn't read crowd, TLDR crowd here, is that they spend half the report lauding the engineers that were working on the telescope, that that despite lack of maintenance and the age of the telescope and lack of funds and all that, these folks would work long hours and all that to keep this telescope running. But to keep the telescope running, they had to start cutting corners. But still, they didn't get the funding. They didn't get any kind of support for that until the predictable surprise, as they say, occurred, and there was an accident. So basically, I look at all these people that kept the telescope running as heroes, and then the report turns around and throws them all under the bus. So it was all their fault and all that. I guess that management gets to write the reports because they turned hero into a dirty word because they literally kept this telescope running, and they were asking for funding, and they just didn't get the repairs that they needed. And so eventually, the predictable surprise occurred, where a problem happened. Okay, so that was a little tangent there. So now I'm going to bring it back to DSES. So we actually, come October, Rick had submitted this. We're kind of assuming we're going to get the RFI accepted. So we kind of started off with one of the things we try to do is we try to do a lot of STEM outreach in eastern Colorado and southeastern Colorado. There's really not much out there in terms of resources. So we try to be a resource for the community. And this is a map to give you an idea of where Eads, Colorado is, which is way out there. I find it kind of interesting that I had just, for someone else, I had looked up the Chamber of Commerce, and so it's showing up as recently searched for, so there's a "You Are Here" sign on this map as well. But Eads is about 2.5 hours east of Colorado Springs. And with the help of a local member out there, is we actually got the Eads Theater, and we did a presentation of the Eads Theater about the Artemis II mission to the community. It was just kind of, we opened it up. They advertised it down in La Junta and as much as far and wide as we could. And Mike Proul, who was the Orion Program Principal Network Architect. So he was the one that basically networked all the machines that are within the Orion capsule, came out to speak. And so he introduced, everyone that showed up to the Orion capsule, the inner workings of the Orion capsule, why NASA's doing what they're doing, and was able to answer a lot of questions. So that was in October. Probably immediately after we had put in the request. So we were able to do some STEM outreach in that area. This is not the only thing. We do a lot of other STEM outreach, which I won't get into. But now that we had our response to the RFI out there, we started looking at what we needed to do to get this dish ready for man-made devices out there. And one of the first questions that kind of cropped up is, this dish is almost 70 years old, so is it still calibrated correctly? So on obviously a cold day, I look at that with envy now with a day like this. On a cold day, we went out there, and if you look really carefully, you can see there are ping pong balls kind of alternating with mirrors on this dish. We had two different ways of characterizing the curvature of the dish. One was photographically, taking two baseline photos and combining them and determining offsets. And the other one was using mirrors and just checking the focus. So we spent a day pasting all these balls up. Actually, the photography and the experiments went on that night when I wasn't there. And the dish shape turned out to be very good. So it's really built very, very well. I mean, when it's taxpayer money, spare no expense. And this was built on taxpayer money way back in the late 50s, early 60s. So it's holding together very well. The next question we had is it focused correctly? Are we actually at the focal point? So this is a really bad picture, typical picture when you hold your cell phone up to a pair of binoculars and take a picture. But if you look right above this pointer, whoops, there's our dish about 8.5 miles away. We have a little transmitter here that's generating, it's just a beacon. It's generating a signal. This happens to be at exactly 180 degrees south of where our dish is. So we were able to make sure that it was pointing correctly, as well as checking out the focal point of the dish itself. By the way, at that distance, about 8.5 miles, 1 degree off is about 800 feet. So, you know, we would be able to tell. It's not as good as focusing on a distant object, which our control team actually does have a calibration where it looks at stellar objects, and it was able to determine the how accurately it's pointing and to tweak those parameters. So we've got the dish kind of checked out at this point. Well, we need some way to receive the signal from the Orion capsule. So this is just a commercial off-the-shelf feed by RF ham design. CIR 12 or 2320. You can just order it right off the web. It's a septum feed, so we're dealing with circularly polarized signals that are coming off of the Orion capsule. And so we got the feed, and then we started designing kind of the RF chain for it. And so here you see there's the left-hand feed, there's a right-hand feed kind of out of the picture here. That comes down into a latching relay. So we can switch between left-hand and right-hand circular polarization to receive the signal. And then this goes into a preamp. Now I'm a software engineer, and one thing I've discovered about good RF engineers is if you ask 4 good RF engineers their opinion on something, over time you will end up with 16 opinions. And there was a very interesting disagreement that occurred about NASA gave us some kind of ambiguous information on whether we were looking for a right-hand or a left-hand circular polarized signal. And so there was a big discussion and all that, and we finally just threw in our hat and said we're going to switch. And so to give you the final answer, it turned out to be right-hand circular polarized in space. So because we're dealing with a dish, let's see if I can get 8 different answers. Right or left-handed circular polarization? Left-handed. Who said that? Well, you get to cheat. There's a reflection. You're reflecting off the dish. So right-hand circular polarization becomes left-hand circular polarization. So it was left-hand circular polarization after all.
What frequency?
S-band, so it was 2214.5, I think it was, or something like that. And so then after we had our first preamp here, then the second preamp, or the preamp fed into a bandpass filter, and then the bandpass filter went into a splitter. Now it turns out we are both experimenting and covering our bases here. So one of the thoughts is you put an SDR up in the hub. You have a very, very short RF path. The SDR is there to process the symbol very, very close to its source. And the other one is that you bring it down via coax into our control room, and you process the signal there. So what we did is off this number 1 port is that we actually had 2 preamps. We ended up getting rid of the second preamp because it overdrove the SDR that was down in the control room. but you basically, we lifted the signal a little bit more before we pumped it down, what, 150 feet of coax or so, down to the control room. This other side does, or went right into the SDR that was inside what we call the hub, which is just behind the focal point. I'll show you some pictures of that in a moment. So kind of the finished product here was, here we have with our high-tech weatherproofing, we have our feed and all the RF signals and all that feed back inside this hub, and I'm going to be giving compliments to a number of people, so forgive me while I give a. This is going to sound like it's kind of I'm doing this for myself, but this is our new feed. We had a new feed mount. There was an older feed mount design which actually worked very well for us for many years, but we weren't changing feeds a lot. We're now getting into the point where we're changing feeds quite often for different frequencies, and handling nuts and bolts 35 feet in the air, it doesn't work very well. This feed, I looked at this problem for a while, and so this is, pardon me while I do this. This feed, or this mount, the feed snaps in, totally toolless, and probably can return a feed within 1 or 2 millimeters of its original position. And if any of you ever need to build anything structurally, this is 3030 aluminum extrusion that works fantastically for keeping things square and keeping things extremely rigid. So if you ever need anything to build anything like that, look at this. They have it both in English measurements as well as I was using metric measurements. So these bars are 30 millimeters by 30 millimeters. In fact, the person who turned me on to this stuff originally is on the Zoom call right now, which is Bob Lord, and so I want to thank Bob for pointing me to that. Let's see. So, yeah, I was down there. So this is the setup inside the hub. So you're looking toward the dish. The dish is kind of beyond this. We have an SDR. We have a Raspberry Pi that's doing control. We've got some other equipment. We actually had a table that the feed sat on that had a screw on it that could actually run the feed in and out to focus it. So there's some equipment in there to run that what we call the Z-axis focus there. So this was the solution up in the hub, and then the information then went down via fiber optics to the control room once it had been already processed by the SDR.
Is all of that equipment changed out if you change frequencies?
Yeah, in fact, this was specifically for the Orion Doppler shift experiment. And actually along the top here you can see again, here's our bandpass filter, here's the splitter, and here are 2 amps. This top output, so again there's a 3 dB loss across the splitter. This upper cable went right to the SDR. This lower one actually went to one of our large LMR 600 that goes down to our control room. Let's see. And so in parallel with, so this was one of the solutions we were chasing. This is Alex's solution, but also down in the control room, we come to Rick's solution. So Rick also had an SDR, but this was once the signal came down into the control room. This is our control rack for the entire our entire setup. And just real quickly here from this picture, over here we have actually the dish control, which is just the dish movement. We kind of have an RF bay here where the coax comes down from the dish. There are various control lines that go back up toward the dish. we have a couple monitors and all that. Over here we have our time stuff, which I will talk about separately. But this is our clock equipment over here. And we have a fairly large computer down here below it for processing. So let's talk about, I'm going to have to get my water here. I always get dry when is it over there? Oh, it's right here in front of me. Good thing it wasn't a snake. So over here on the left is our control. It runs off of a computer and the software is just called System 1. There's some history behind that, which I won't go into, but the dish is run under computer control normally. But we do have up here the old manual panel. So we're able to actually, with toggle switches, run the dish azimuth and elevation. And we'll come back to that, foreshadowing here. So this is kind of the System 1 software that displays what it's tracking. Now, as I mentioned, we were all set up for tracking celestial objects, things that are fairly easy to predict, like the moon and all that. But now we're going to be tracking a man-made object, and it doesn't behave like these big celestial objects do. So the System 1 folks went off and came up with a very interesting solution to this. I'm thinking about, are they going to have to, model all of the orbital mechanics of all this in order to predict it? Well, there's a shortcut. There's something called the JPL Horizon System. And the JPL Horizon System, you can ask it to track basically any man-made object out there, and or celestial objects as well, or planetary objects, I should say. And JPL, you can actually interrogate the JPL site and get an azimuth and elevation for that object at any point in time. So what they did is they modified their software to constantly interrogate JPL horizons and move the scope to the azimuth and elevation that JPL Horizons was telling them to do. I mean, it was all new functionality that they had to add to their software. And to give you an example, if you go to JPL Horizons, you can tell it to pick an object and give it the azimuth and elevations for whatever time interval. So this actually is the Mars Reconnaissance Orbiter I just brought up. I can't do Artemis anymore. Yes?
Does it take into account the latitude and longitude of the antenna?
Yep. That's something you give it. And elevation, and your elevation. So latitude, longitude, and elevation of the observer, and it will give you the exact azimuth and elevation. I couldn't, to do an example, I can't do Artemis because Artemis isn't up there anymore. So I did Mars Reconnaissance Orbiter. But this shows you, this is actually today's information. I think it was 3 hours that I set it up for. So if you Google JPL Horizons, this can come up. And if any of you have optical telescopes, you could possibly use this to drive your optical telescope to perhaps see satellites. So it's just something that you might be interested in trying out. Their end product was this dot that would say Artemis, and there's a circle, and that circle is our 3 dB drop-off. As long as the object is within that circle, we will have less than a 3 dB drop-off of power. Now, the great thing about Artemis is it's actually transmitting. I mean, we've done moon bounce, so you transmit the signal out, and this tiny signal comes back at you, and we can get that. So actually pointing ourselves at a transmitter, we're getting a lot of power from it. So even if we wandered outside a little bit of this 3 dB circle, we were receiving it just fine. But this shows you as the software's tracking in on Artemis, it finally comes in, and then the software automatically just keeps that Artemis within that circle. Now, because it's an azimuth and elevation telescope, we can't track it nicely like a clock drive. So this is Bill Miller's term. He calls it bang bang positioning. So we wait until Artemis gets like right toward the edge of the circle, and then it does a bang bang positioning, and it drags it back to the into the middle of the circle, and then stops again and lets it drift. So we're constantly starting and stopping our telescope to track these things.
Roger, how often do you have to do that, bang, bang?
I'm going to give you a round number. Fif-
Depends a lot on the elevation.
Yeah, 15 to 30 seconds.
In this case, yeah, about 30 seconds.
Yep, it's not too bad.
Roger?
Yes.
Are you monitoring a beacon or just when there is transmission, voice transmission? What are you actually listening to?
So Rick, you might be able to fill this in a little bit better.
Listening to digital telemetry.
Okay.
And there is, oddly enough, they didn't tell us this, but they had a carrier turned on in the middle of it to make it easy. They didn't have to do that, but they did. We didn't know that till we looked at the spectrum. They didn't tell us anything.
Yeah, I will return to this. They didn't tell us here in a bit. I mentioned kind of up front about how NASA didn't really give us a lot of information, because I think a lot of it is unwritten and understood among the major contractors. So let's turn our attention. So now we have the way to receive it that we've worked on. We now can point our telescope at it. We have one of our two ways of receiving the information and processing it. But we need a very, very accurate time to report to NASA, which brings us to the right side of the bench. So this is our rubidium clock standard. This was actually donated by Art Seppin. Did I pronounce that name right?
Yes, he's on the.
Oh, thank you, Art. Thank you very, very much. With Rick's help, this is right up Rick's alley, he installed this down at the site, and along with an interval timer. So it's for people who want numbers. The rubidium standard is an HP 5065A refurbished. Is that fair to say? And an HP 131A time interval counter. The CNS clock that you see there is by Rick's company, CNS Systems, and there's a Stanford Research distribution amplifier, which then distributes the clock signals to all the devices that need it, which is going to be both up in the tower and where the SDR is collecting the information up there, and to Rick's SDR, which is down in the control room. So let's see. So now we've pretty much got all of our ducks in a row. So we come back to Artemis. About mid-January, approximately 2 weeks before the first launch window, we get accepted to be part of this experiment. We are not ready. And in fact, we all realize we are not going to be ready by the first February launch date. So, as we were scrambled as much as we could. We just weren't. We just could not do it. Fortunately, if you remember, there was a helium leak in the SLS system. So because of that, they rolled the rocket back. We all breathed a sigh of relief, and we're able to get the rest of our ducks in a row for the launch. So the next launch window was April 1st. So we actually were pretty much ready about mid-March or so. Let me go over here.
We actually missed 2 or maybe 3 launch windows, right?
Well, they skipped a couple because,
Skipped them.
yeah.
There was 2 that were leaks, and we
So, on April 1st, a date that has given flat earthers and moon deniers so much ammunition, I wish they hadn't done it on that day, they launched. And by this time, I don't know exactly how it happened, but somehow I became the coordinator for staffing at the site, to get volunteers down to the site to actually monitor this signal. And the problem is we didn't know when they were going to launch until they launched. And I kind of, since I had de facto become kind of in charge, I looked at this, and the first 24 hours, so there's the launch, and it goes around, and then it takes it about 24 hours before the translunar injection, or TLI burn, happens. And because this first very eccentric orbit was so odd that I decided we're not going to even try to monitor it during that time. Because if it's above us when it's at its closest approach, which was about 115 miles, it's nearly at escape velocity. It's not going at ISS speeds, it's going at near escape velocity speeds. And we just didn't know if our dish could track that. And we didn't know when it was going to be up in the sky. There were a whole bunch of problems. So I said, nothing for 24 hours. That will also give me a time to see if we can line up people to go down there. So basically our monitoring was going to be on the way out and on the way back. And again, we were going to skip the last 24 hours just because it was getting close to the Earth and we didn't really know if it was going to be above the horizon or anything like that. Everything out to the moon and back was very, very predictable. It was more or less when the moon was above the horizon. And by the way, artists like this have all these really artsy looking things. Here, I'm going to step, since your camera's going on here. This was a very, very simple trajectory. If this is the Earth, they took a rock and they threw it straight up. The moon happened to duck between it, between us and the capsule, and then it fell straight back down to Earth and it re-entered. It was literally a straight out and straight back mission. And they do have these nice swoopy curves to make it look pretty, but it was straight out and straight back. So it launches, and I am amazed to this day. We had lots of people step up to be willing to drive down to Haswell and spend their 24 hours or so down there. What added insult to injury is that the capsule was conveniently above the horizon from approximately midnight to 9 a.m. So we had to monitor this thing from midnight to 9 a.m. So not only did these people go down to Haswell, but they were up all night monitoring. And so myself and Lewis, by the way, I didn't mention the names of the System 1 team. So our System 1 folks were Phil Gage, Glenn Davis, thank you, and Lewis Putnam. And they were the ones that were able to set up the computer to track Artemis. So Lewis and I, because he's the guidance system, and I'm a warm body that kind of knows what's going on with the equipment, we went down there for the first night, and we couldn't get anything. We were getting absolutely nothing. And so we messed with it and messed with it. Well, another thing NASA didn't tell us was they wanted us to monitor from this time to this time. And oh, by the way, we're not going to be transmitting all the time. They didn't tell us that. So they had the monitoring windows, but so we struggled for a while, probably with absolutely no signal. And unfortunately, we introduced a fairly bad error in our z-axis focus as we were trying to mess around with focus here. So it turned out at the very, very end of the monitoring window, we saw a very weak carrier. And so we were able to get a little bit of data on that first night, but that was literally, 9 hours for approximately 2 minutes worth of data, right at the very end. And we probably would have gotten more, but by then we had defocused the feed so much because of a bunch of errors I'm not going to go into, that we had, we weren't going to get anywhere. And when we started to suspect that they weren't transmitting, this is another cool site that you might be interested in. It's called DSN Now, or Deep Space Network Now. And you can go there and you can see what spacecraft they're communicating with, either receiving from or transmitting to. Very simple graphics here to understand. If you see like 2 waves like this, it's both transmitting and receiving. If you just see a single wave like this, if this was a live page, you'd see it moving out or you'd see it moving in, whether they're transmitting or receiving. What's kind of cool is I did this earlier today, and look here. Down in, or over in Madrid, the DSN, what is that, 63 telescope is actually receiving signals from Voyager, which right now are taking approximately 23 hours to get here, probably a little bit more. In November, Voyager will reach the 1 light day away from us point, which is pretty amazing. And Voyager 1 is actually one of the objects that we're going to try to receive at some point in time. That's kind of on our to-do list. Oh, down here, Goldstone, Deep Space Network, Telescope 14. It's not being used. Can anyone tell me why? It's broken. So if we go back to the schedule, so Lewis and I were down there on Friday the 3rd. By the way, when I say we were down there from Friday the 3rd, that's midnight to 9 a.m. Friday the 3rd. We packed up and left. And where's a microphone here? Bill, why don't you come up here? And so with feed in the wrong position and all that, we turned it over to Bill on the 4th.
I think this is
I turned it on.
okay. All right. Okay. Well,
Hold it up and talk into it. Yeah,
so we were ready to.
it should be.
Is it on? Is there a green light? Where's the green light? Then it's not on. Okay, that helps. Okay, so we went down there on, I believe I got there on Friday, right?
Go back a slide. Hit
back
up
a
arrow.
Okay. Yeah.
You got down there on Friday.
Yeah,
Your
so
first shift was Saturday.
So on Friday, so got down there, and Roger had problems with the signal strength, and so we were getting really low signal, and there was this big argument about where the focal point on the dish was. So I looked at it and I said, well, I remember where the focal point is, so I just moved it and put it back at the focal point. So we put the feed in the right place, and then we had 20 dB of signal noise ratio. So that worked out much better, and we had really good signal. And the spacecraft was transmitting. So that helped. We were ready to track, and so myself, Mario Bandera, and Travis Lightsey, we logged good data for about 8 hours on the morning April 4th. And, okay. And so from midnight to 8 a.m., we got good data almost the entire night. And so we were really very confident that we could easily track, and we got good signal to noise ratio, and our automated system was working well, with augmented by the NASA JPL Horizon site, and everything's going great. And we said, well, let's finish off for that day. And so we slept a little that day and put some shrimp on the Barbie the next evening and had some shrimp. And we're super confident, and we're going to have a great night the next night. And so we bedded down, slept a little more, and the shift didn't start till around midnight on April 5th, which is Easter morning. And so we decided, well, I was first to get up, and I said, well, I'll just let the other two guys sleep, and I'll fire up the dish, and we'll get in there and we'll start tracking. So I fire it up, and I initialized the system and started the slew. We had to walk it around from the 317 park position around towards the west and then all the way around towards the east where the Orion spacecraft was going to come up on the horizon. And I thought, boy, it's working. I see it moving. I walked out into the quiet evening just to admire the dish as it was. You know, here we got this 30-foot or 60-foot, 65-ton object moving in concert with our electronics, and that's pretty thrilling when you get out there and watch it. And so I said, this will be great, and I walked out the door, and I said, wait a minute, it's moving counterclockwise, and it should be, or it's moving clockwise, and it should be moving counterclockwise to move all the way around the arc. And I panicked, right? I said, uh-oh, so something's wrong, it's going the wrong way. So I shut down everything, I checked it, and that's where I get this quote from Star Wars, great kid, don't get cocky, right? Because we thought we had it, and everything was going to work perfectly the first time. And we had one good night, the next one was going to be good. So I shut everything down, rebooted the computers, rebooted the dish, rebooted everything, and it did it twice in a row, going the wrong way. So I quickly woke up Mario and Travis, and I asked them for assistance, and we went through everything and troubleshot the system, and we couldn't figure out what was really wrong. So after about an hour of troubleshooting, I sent a message to the entire DSES tracking team, and I said, Houston, we have a problem, and it was broken. And Glenn Davis, who is the head of our tracking group that did all the control systems for this, he happened to be on vacation in Hawaii. And of course, Hawaii is quite a few hours behind us. So here I am at about 1 o'clock in the morning, and I send this message, and Glenn's online looking at email, and he calls me right up on the phone. And he says, what's wrong, Bill? And I said, well, something's wrong. We're tracking the wrong direction, and it's telling me we're going counterclockwise when we're actually going clockwise. And he says, okay, so he walked through it with me. We did all this work, and he says, well, I think it's the LabJack. We have a LabJack general-purpose I/O module. I don't know if any of you are familiar with LabJack, but it's an instrumentation module that you can get voltages in and out of and do analog to digital conversion and all that. So he says, that's broken. And so, but I've got a spare, he says, but it's in my house, and I'm in Hawaii. So he gave Louis Putman, his cohort, permission to go break into his house and get it out that morning. And Louis did, and he and Paul Solman and Jeff Flegnon, they rushed down to the site with that spare and installed it Easter afternoon, and but it didn't fix it. So we're still down, okay? So scratched our heads, did some more troubleshooting, kept working on it, couldn't figure it out. In the meantime, Rich Hambley back here and Alex Nersessian, they were monitoring the signals remote, and they were redoing the software to get a better and better lock on the signal and a better display of the signals that we were receiving off of the satellite. And so they had had problems too, and they weren't happy with what they were getting out of their equipment. And so they kept improving the data and the software, and I think they went through 13 versions of over the course of the mission of software. Oops, I messed it up. Let me get the cursor out of the way. There, got it. Okay, so now while we're trying to fix the system, so several days of tracking data we missed because we were down and the automatic tracking wouldn't work, and nobody could figure out what to do. And so we're in a quagmire, and then Roger comes up with this brilliant idea, out of the box idea, so I'm going to let him tell you about it.
so we were kind of stuck. But one of the things that Bill discovered is that the manual controls, our old manual controls, he dusted them off, hooked things up, and the manual controls worked just fine. So I was kind of thinking about this, and it's like, well, the software that's supposed to track the Artemis, it may not be able to drive the telescope correctly, but it shows where Artemis is in that 3 dB circle. So if all we do is use that for our positioning information, we can actually manually control the dish and follow it, which is why I kind of know the answer to your question about 15 to 30 seconds, because our nights became 9 hours of 15 to 30 seconds apart of flipping these switches to track the Artemis. So, I mean, it ended up kind of looking like this, where again, just like the computer would do it, we'd let it drift right to the edge of the circle. We were a little more proactive than the computer, because if it reached the edge of the, I guess I could do it with the laser. If it reached the edge of the circle over here, we could actually drive it all the way over to this edge of the circle and then wait for it to track all the way across. So if I go back to the schedule here, here's where Bill had the problem, was the morning of the 5th. Paul Saban, our president, and a couple people went down and did a lot of debug and all that on the 6th. I called the folks who were supposed to work on the 7th and told them, just don't go. We're trying to figure out the problem. And on the 7th is when I kind of got this idea of, I think we can track this ourselves. So starting on the 8th, I went down along with Ann Haney and Larry Stewart from Chicago. We had someone come out all the way from Chicago to do this. And one of our relatively new members, Richie Larry, which I actually knew from work, came down there. And we, for 9 hours, drove this telescope. And Richie left early the next morning because he had lunch. He had a lunch with a group of people. And he went back to that group of people, told them about, the words he used was, it was the world's most boring video game of keeping this thing inside the circle. And of all things, Tom Eggers here in the front row was at that lunch and got interested in the world's most boring video game enough that he called up and said, "Can I come down and run it?" So Tom joined us the second day, and so those last 2 days we were able to get good data. Good data when they were transmitting. By then we knew that we weren't going to see the signal all the time. And then comes the 10th is when it was the capsule was coming back in and returning. So we didn't staff the antenna at that point in time. So let's talk about the data we got here real quick. And what I'm going to do is, if I can get the mic and show me how to get the green light on, I'm going to give this to Rick, who can describe this far better than I can, and I'm going to be taking notes so I can do this better next time. Go ahead.
Thank you, Roger, for not showing me these slides.
I know.
So I have no idea what's coming. But that is one of our spectrum displays.
Hold it.
What happened?
I thought it was on.
It's on.
I thought you handed it to me.
I see. There's on, and then there's more on. Okay. Well, we wrote our RF and software team wrote all our own software, and one of the things we displayed was the spectrum display showing the bandpass of the SDR in its native mode, which is the bandwidth is based on the sampling rate of the A to D in the SDR, and that's adjustable. But that's all set up looking for Artemis. Now the signal in the middle is the standard SDR 0 pulse, which you always ignore. But we had that other little signal to the right, and that's the transmission from the Orion capsule. So it's substantially above the noise, so we should have no excuse but to get all of our data perfect with that kind of a very strong signal and no RF interference within our passband. Now, this is taking the time display of the frequency to show you that, yes, there is Doppler shift, which is a change in frequency over time. And this is one of our better passes where we had a fairly good display of Doppler shift and very little noise in our data, which is exactly what they were hoping to see. It's not a perfect straight line, but that's exactly right, because we're looking at the spacecraft not straight on, but as it moves on its path. So that's one of our better data sets. And this is raw data and smooth data showing the same kind of frequency offsets. And this is the kind of data that needed to be put into data sets and sent off to NASA. And when we saw this, we were pretty happy that we were finally getting data that was meaningful.
Thank you, Rick. And so those last three slides were Rick's data. This is the SDR that was down in the control room. And this is the data that was coming from the SDR that was up in the hub, which is Alex's data. And you can see, they were using the same software, and they were seeing kind of the same trends for the.
Not the same software, right? These are two.
Well, you had an overlap.
They are related. At that point, I had not written my own from scratch, but I did take liberties. Most of that software is Python wrappers over the top of Radio Conda libraries.
Sorry about that.
It's all pretty much the same stuff.
Here, I'll just leave this with you in case something comes up again. So we're going to do full circle. You've already seen this. Ultimately, what NASA wanted was very accurate time from an atomic clock and the carrier frequency that we were reading. They didn't want any processing. What? Whoop. Go ahead.
NASA, again, didn't tell us anything. What I mean by that is we asked them, what kind of data do you want? When do you want it? Do you want it in real time? Do you want it immediately after each transmission block? Do you want it every day? When do you want it? And how does it look? So they gave us a specification. I've been in this business all my life, a government specification that even I couldn't read. And so we went round and round, and that is the result. The good news is they didn't want it till after the mission landed. And then they didn't want, they said they wanted Doppler. We keep using that word. They said, no, don't send us any Doppler, please. Don't do that. Because that means you have to do math. Let us do the math. So that all the numbers there are frequencies. They said, we don't care what your frequency is, only what the changes in frequency are. So they didn't want us to touch anything,
Yep, so,
except we had the wrong date on there, so I had to touch something. We had some mistakes in our software. So I cleaned it up a little bit before I said it, and that's the result.
so yeah, the ultimate delivery to NASA was the date and a very, very accurate time in this column, and the frequency in the second column, and that's it. So NASA actually got to crunch the numbers. They didn't trust anyone else to crunch the numbers, and I can see why they would want to do that themselves. So to answer Hans's original request,
It was a simple question.
that yes, that's what we delivered to NASA, was a file with time or date, time, and frequency. What's that? I don't know how, you know, they're going to look at all of the input that they got, and they're probably going to experiment to see how well they can triangulate and all that, find out who did it right and who did it wrong, and all of that, you know. So I'm not quite sure how they're post-processing it. I mean, they didn't tell us how to do it, so, you know.
Do you know how many inputs they were getting?
How many, what,
were
30-some sites worldwide?
There were, yes, I think 35 sites, and when there were transmissions, every line is 1 second, although they left that up to us also. They didn't tell us what the time interval between data's items were, but 1 file per transmission block. That's how I separated them. So there's a half a dozen or a dozen files, and 1 second per line, and these are fairly large files.
Mm-hmm. So, all said and done, do you remember what I told you the difference between an RFP and an RFI was? Yeah, your request for information, you don't get paid, but you do get a certificate of recognition. So, you know, Deep Space Exploration Society got a certificate of recognition from NASA for participating. We are actually quite honored that we were like one of 35 locations worldwide that got accepted to do this study. And I will kind of end things with the fact that Artemis 3 is going to be going up probably a little bit more than a year from now, year to year and a half from now. It's going to be a low Earth orbit mission. Unlike its originally planned mission, NASA got a reality check and is going to try doing all their docking maneuvers, just like the Apollo program. Do all the docking maneuvers in low Earth orbit and shake the problems out there. We haven't decided yet. I kind of hope that we participate in this, but the nice thing about this is that we don't have to use the dish. It's low Earth orbit. We can use probably a Yaesu azimuth elevation mount with a good Yagi on it, and you know, and that we can run remotely. So we always require people to be on site when the dish is running. For what Bill found out, he goes out with his cup of coffee, looks up at the dish, and goes, "Wrong way." So that's why we have to have folks on site. So are there any questions?
I have a comment.
Okay.
Had we not caught the dish, like we would have run it into the stops, right? And it does have, yeah, what I was
Start
saying
over again.
was had we not caught the dish going the wrong way, we would have run it into the limit, first the limit switches, and if those failed, it would have run, well, we would have run into the software limit switches, then the hardware limit switches, and then the hard stops.
You'd have done a Goldstone.
We would have done a Goldstone.
Mm-hmm.
Yeah, so you don't want to do that. And that's why we have a rule that there's always got to be 2 people on site. If you're driving the dish, you got to be monitoring the dish visually. We're going to do some monitors and stuff to make that better, but you got to watch that dish because you don't want to wrap it up.
Did
Sorry.
you ever figure out the clockwise, counterclockwise situation?
Yes, so he mentioned the lab DAC that was replaced. Well, the lab DAC has a little daughter card on it, which is it's a digital to analog converter. Oops, let me just get over here and stop moving. Digital analog converter. For those that aren't familiar with it, think of it as a volume knob. It's actually kind of the same thing we ran it manually with, and that DAC, we haven't gotten a root cause on it, but that DAC failed, and so it was sending out the wrong voltage. The azimuth is run with a very simple DAC that outputs realistically probably from about -3 volts to +3 volts. That range of voltage goes into a motor controller, which translates to how the motors run either clockwise or counterclockwise. And it was stuck putting out the same polarity voltage. And the nasty thing about it is we have lights that show whether it's turning clockwise or counterclockwise. It was showing that it was turning counterclockwise. Well, the dish itself was turning clockwise. So
So at that point, Roger decided to redesign the whole control system.
yeah.
And so he's working on that.
You know that little board I brought that in. I think it was for show and tell. That's what kind of inspired me to I was a diagnostic engineer, so given that I wanted to design a system that actually looked at what things were doing rather than assuming that they were doing those things, and so that's kind of why I'm working on that. Whether it replaces that system or not, who knows? But I'm having fun. Yeah.
So based on everything that you presented us with,
Uh-oh.
if you went to that JPL site and had motor control,
There's a mic right there.
oh, if you accessed the JPL site, had motor control on a Yagi, you could track an amateur radio satellite the same way?
Yep.
Yeah, that's kind of, and that System 1 software, where does that come into play and where's that obtained and stuff?
It's homegrown software. It's probably written, what, 5, 8 years ago?
It's been in progress for 10 years.
10 years, okay.
It's still in progress.
But given like the Yaesu As-L mount or something like that, you probably could write a fairly simple program that would interrogate the JPL site and then just send the correct azimuth and elevation
So it's
to your
just an
mount.
API going out to JPL site?
Yep. At least by my understanding, yeah. I kept you later than I wanted to. Sorry about that. Any other questions?
Whole other discussion. How would AI have impacted this exercise?
Actually, a lot of AI was used. Alex, who did a lot of the software so his equipment was the equipment that was up in the hub, and Rick used some of it, was written by AI. So he had AI writing a lot of his software, which is one reason why I think Rick mentioned that they went through 13 versions in about like a day or two, as they kind of homed in on it. I mean, there's so many different areas. I don't know what area you're asking about AI.
This is an esoteric question, but I wonder, you guys have all been trained and worked in these fields for generations, for decades. That enabled you to figure things out. And I'm fascinated by AI, and I'm wondering if there's a weak link there, that without this formal training, will it master what they think it's going to master? That's a whole other conversation.
Yeah, well, I got a comment on that. One of the things that happened when we were designing the feed, Alex used AI to design a horn for the feed antenna. So what's our frequency? 24, 14 and a half.
22,
22,
15,
14 and a half.
14 and a half, I think.
And so he used AI to design the feed cone that went into the little square antenna, right? And we looked at that and we weren't getting good results with that. And I took it home and I'm characterized it in my yard with the beacon transmitter. And I said, wait a minute, this isn't working. Why is it not working? And so I look up the equations that he used, and I said, wait a minute, you know, he's got the wrong thing there. So by using AI to design, and he insisted that that was the right horn, right? But so unless you're really knowledgeable and you do some testing, you're gonna error all over the place using just AI, right? And so we ended up taking that clear off, the horn antenna on the front of the feed antenna. We took it clear away, and then we got really good gain. And that was what the company that designed the feed antenna said we should get, and it all worked out. But that's not the only time we've had AI send us down the wrong path. So you got to know what you're doing as well. But AI can really speed up the process.
Good for grant work.
Yeah. Yeah.
Yeah, trust but verify.
You know, I would hazard a guess that if you asked, I want to track this satellite, you know, how would I get its coordinates? That I bet one thing that AI would probably spit back at you is the JPL Horizon stuff. If you didn't know about it, I didn't know about it until they started showing us what they were doing with their tracking software. So that was a big eye-opening experience for me about that site being out there.
AI is a trainee that you have to monitor.
Yes. it's the intern.
Yeah, intern.
Yeah.
I didn't come up with the word I was.
Yeah. Anything else? Well, thank you very much.